Okay, welcome back. We have been talking about the derivative. Last time we defined the derivative. We said what it means for a function to be differentiable, which basically means that a certain limit exists, right? It's a limit of a difference quotient. The difference quotient represents the slope of a secant line. And we say a function is differentiable at a point x if the limiting slope of a secant line actually exists. And we also, last time, talked about a very, very important theorem, which basically is the most important theorem when it comes to derivatives. It connects the value of the function to the value of derivative. And what was the name of that theorem? Mean value theorem. Good. So today I want to convince you that it's actually an important theorem and talk about generalization known as Taylor's theorem. So that's the first part of the lecture. And then the second part of the lecture, I want to discuss sequences of functions, which is a different topic. So let's see if I remember how to turn the lights on here. There we go. Great. So let me say what Taylor's theorem is. And hopefully you'll see it's actually a generalization of the mean value theorem. So here's a statement of Taylor's theorem. Well, actually, let me motivate it a little bit. So the idea is that suppose you know something about a function and what it's doing at a particular point. The idea of Taylor's theorem is, well, if you know something about what's happening at a point, you know what's happening near a point. If the function is differentiable or twice differentiable, or if you have a number of derivatives. So in the simplest case, suppose you know something like what the function is doing at a point A. And maybe you know, well, let's suppose you know what's happening at A, and you want to approximate what's happening near A, let's say f of B. Well, the mean value theorem tells us something about f of B if you know f of A and if you know the derivative nearby. Okay? So the mean value theorem basically says, oh yeah, I can figure out what f of B is if I know f of A and I know something about the derivative nearby. Okay, so this is a restatement of the mean value theorem. And the thing to notice here is that there is a mysterious point C, and all we know about C is that what? It lives between A and B. Okay? Okay, for some C in A and B. Okay. Now, of course, we don't really necessarily know what this point is. And so the way to think about this is I know f of B if I know f of A, and, well, okay, I don't have that much control over this term. This term is something like an error term, right? It tells me how far off f of B is from f of A. It's like an error term. It's not precisely known necessarily. Often it's not. But it has something to do with the derivative nearby. So if I can bound the derivative nearby, then maybe I can actually say something about this error. Okay? That's one way to think about the mean value theorem. So this actually suggests that I might be able to do better with my approximation if I look at, let's say, f of B and f of A. Well, f prime, I don't know what it's doing at C. I don't even know where C is. But what if I knew what the derivative was doing at A? Then maybe I could do better, right? Maybe this suggests that f of B equals f of A plus maybe f prime at A times B minus A. Was it going to be exactly this? No, maybe there's some error. another error. Hopefully a smaller error term than before, right? So this is another error. So it suggests that there might be a theorem like this, right? So here's a question. Can I fill this in suitably? And the answer is, yeah. Well, if the function actually has two derivatives, if it's twice differentiable, then in fact, there is an expression that will make this an equality, namely the derivative, the second derivative, over 2 times b minus a squared. And this is evaluated at some mysterious point, c. Not the same c as the original, the first statement. It's just some c in between a and b. Okay. So, yeah, there is a expression. Notice this error term's a little better. Because if b minus a is really small, this thing's small. And once again, I have no control over where c is. All I know is that c is somewhere in between a and b. Okay? Okay. So this is the direction that Taylor's theorem goes in. It gives me some idea of how good this particular error term is. So what's the moral? The moral of the story is, if I know the function value and its derivative, and at a point A, and I know what its second derivative is in some neighborhood of A, then I will have a good handle on what f of b is. Okay? Okay, great. So let me just say more generally then what we can say. So more generally, I mean, you could continue this process, right? You could say, oh, wait a minute. This error is kind of like a second derivative. So maybe if I throw in a term like this at a, where c is replaced by a, I'll get still yet a better error term. That's really the direction that Taylor's theorem goes into. So suppose I define a polynomial I'll call p sub n minus 1, which is basically, so it's a polynomial in x, and its first term is f of a. Its second term is f prime at a times x minus a. Its third term is the second derivative at a over 2, and that's secretly a 2 factorial. So this is 2 factorial, which is 2, times x minus a squared, plus dot, 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 and let's continue until we get to the n minus 1th term. So this is f. The nth derivative is notated with a exponent, but in parentheses, at a over n minus 1 factorial times x minus a to the n minus 1. Okay, so here's what I want you to notice. Where do the x's appear here? There's an x here. There's nothing in this term, so it's constant with respect to x. There's an x here. What's in here? An x squared. And there's some x's floating around here, but this is a So the point here is, you see you have polynomial in x. Okay? Okay. And what's degree? What's its degree? Good. N minus 1. Very good. And what's the dependence on a? Well, notice, in order to figure out what the coefficients are, this is really polynomial in x minus a, and the coefficients all involve derivatives at a, value and derivatives at a. Okay, so this is a polynomial, sometimes called the Taylor polynomial. Okay, so here's the content of Taylor's theorem. So Taylor's theorem says, if you have a function, this is a real valued function, and let's say it's a function that's continuous. Okay, what do we need? Well, we want the function to be defined. We want its derivatives to be defined up through the n-1th derivative. Okay. So, of course, if you have the n-1th derivative, you have the previous ones, right? So I don't need to say that. So what we're going to demand is that the n-1th derivative, the very last one you need, we're going to demand that this be continuous, okay, on AB. So I'm demanding that on the closed interval AB, this function has a continuous n-1th derivative. And I'm going to demand that the nth derivative exists. I don't need it to be continuous, but I'll demand that it exists on open AB. Then, something amazing is true. First of all, Pn-1 is a polynomial, so it approximates f. That's the message here. Approximates f of x. In fact, it's going to be an excellent polynomial approximation. How excellent? It's going to be this excellent. If you have f of x, it's going to be, well, I can write it as the polynomial Pn-1 of x plus an error term. What's that error term, that mysterious error term? I claim this is going to be really quite small. So what's it going to be? Well, it'll be the nth derivative at some mysterious point C. We have no idea where that point is, except what that is exactly. But I do know that it will live between, where? Take a guess. Yep, A and B. And then, of course, this gets multiplied by x minus a to the nth. Okay? So this term looks a lot like the terms of the Taylor polynomial, except that the nth derivative is evaluated somewhere in between a and b. Okay? Okay, so let's just step back a second. What does this theorem say in the case that, what does this theorem say in the case that n is 1? Can you prove this theorem in the case n equals 1? Yes, what is it? F of... So what's P0? It's just f of a. Good, so we're saying that this function is just, tell me what is going on at f at a, and then add what? F prime at c over 1 factorial times x minus a. Is that true for some c? By the? Good. This is the mean value theorem when n equals 1. So the first remark is, when n equals 1, this is the mean value theorem. Taylor's theorem is just a generalization of the mean value theorem. Okay, let's see. Second comment. I've said it already, but Pn is basically a polynomial, and it's the best polynomial approximation. The best polynomial approximation of order n at a. Okay, now what do I mean by best here? Well, what I mean is I've constructed a polynomial that has all the same value and derivatives up to the nth. Same value of f prime, f double prime, dot, 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 through f super n at a. Same value of, let's see, okay, so I mean same value of this and p prime, p double prime, p the nth derivative at a. So in other words, these things all correspond. Okay, the first derivative of the polynomial, first derivative of f, actually has the same value at a. Let's just convince ourselves of that. Look at this polynomial here. If I look at its value at a, what happens when I plug in x equals a? 0, 0, 0. All this is 0. So you just get, at a, this is f of a, right? What happens if I take the first derivative of p? What happens to the f of a term? This disappears because derivative with respect to x is gone, yeah? Now, of course, what happens to this when you take the derivative with respect to x? Just get that times 1, right? Okay. And then the rest of these, would you agree, have powers of x minus a in them. So when you plug in x equals a, all the rest of the terms with their derivatives disappear as well. So the derivative of p is the same as f prime at a. Similarly, you take the second derivative, notice what happens. These things vanish because it only has, it's a linear in x, so it'll vanish when you take two derivatives. This term survives, and these terms all vanish because x equals a. Why did this thing, can you see why we needed the 2 factorial here? To cancel the powers that come down when you take the derivative twice. If you want the nth derivative to come to match up, then you need the the nth factorial underneath, right? Okay, that's really where it comes from. Excellent. Okay, so how do we prove this? Take a wild guess. Oh yeah, okay, induction. Mean value theorem. Yeah, you can definitely do it by induction in the mean value theorem. I'm actually going to do it slightly differently than the book does. So yeah, the proof, the book actually has a proof, but I'm going to do a different proof. This one I actually like better. So would you agree with the following statement? Clearly, clearly, yeah, do you agree with that? It's all clear. For some number m, would you agree that for some number m, the following must be true? For some number m, check this out, f of b, let's compare that to the value of the Taylor polynomial at b. So f of b is Pn of b plus something, right? You can't stop me from writing f of b this way, right? This is the value of f at some point b. It's a number. This is the value of the polynomial at b. That's some number, yeah? Okay. Well, would you agree that b minus a is also some number? Yes? I'll raise it to the nth power. That's some number. And for some suitable choice of m, this statement is true. Yes? I didn't say anything with any deep content, right? Number equals number plus something times number. You can solve for something, right? Okay. Okay. But, so clearly, for some number m, this is true. I'm going to refer to this equation as Cyclops Smiley. Okay, so let's look at the following function. Let's look at some function I'll call g of x. Okay, now I'm introducing a variable here. So let's see. I'm going to call define a function g of x, which will be f at x, so that's the original function I'm interested in, minus the polynomial at x. Hopefully these are quite close, yes? This polynomial is the thing I'm comparing it to. Yeah? Okay. I hope this is small. Are these going to be equal? No, not necessarily. So let me subtract off m, for that number m you said was clearly existed, times x minus a to the n. Okay, now, why in the world would I do this? Well, it's maybe not clear yet. It'll become clear soon, but you can't stop me from defining this function. Okay? And what am I hoping? I mean, where is this headed? Well, it would be nice if I could show that g of x were 0 somewhere, yes? And maybe m was this coefficient, right? It would be nice. Okay, check this out. So look at what happens when I take the nth derivative of g. What happens when I take the nth derivative? Well, would you agree this is the nth derivative of f? Minus, help, 0. I'm going to ignore it. Thank you. And the nth derivative here, m. This is so cool. What's the nth derivative? N factorial, and that's it. So the nth derivative of x is just f to the n of x minus m times n factorial. And what I claim then is it's enough to show, what I'm trying to do is, will certainly be enough to show that g sub n of some point c is 0 for some c. For some c in between a and b. Why would that be enough for what I'm interested in? If I could show that this creature were 0 somewhere, that would make fn of c equal to m times n factorial. So that would establish that m is in fact f, the nth derivative at some point c over n factorial. Okay. And what would that do? Well, let's see. I'm kind of, yeah. Well, so that would be nice because then the thing that I'm interested in, this expression, would actually be what? Well, I'm hoping this thing is actually equal and this thing's going to be 0. Okay. So let's just see what happens here. So we can check a few things about g. So the nice thing here is, tell me, this function g, what is its value at a? What is this function's value at a? A minus a is 0. F of a minus Pn minus 1 at a. Why is it 0? They have the same value, right, at a. If I plug in a here, these things vanish. So g of a, in fact, is going to be 0, since f at a equals p sub n minus 1 at a. You can check that. Right? Okay. Okay. What if I take the derivative of g prime, and plug in a? Well, let's see. This is the first derivative at a is the first derivative of f at a minus m times 1 factorial at a, g prime at a. What do you get? What is g prime at a? 0. Why? Good. Okay. So, yeah, right. So, right, this is the nth derivative at right. So if I take the derivative here, I get g prime at x minus f prime at x minus the first derivative at x minus m and the n. Right. Sorry. That was just the nth term, but I want the first term. Right. So this vanishes, and f prime and p prime have the same value. That's basically what we see. So, in fact, if I look at the second derivative, I'll also get 0. Why? Because f prime and p prime have the same value at a, and this one's true because f double prime at a is the same as p double prime at a, etc. So in fact, what I've done is I've constructed a function that's very, very flat at a, right? I mean, up through the n minus 1th derivative. Okay? So this is an important fact. G is very, very flat at a. Okay. Well, what else do you notice? Well, check this out. What if I look at g of b? What happens when I plug in x equals b here? B, B, B. Why is it 0? Yes, Smiley shows that this is 0 by Cyclops Smiley. Right? That's the definition of M made this true. Okay, so here's what I have. I have a, here's the point A, here's the point B, and I know that at A, G prime is 0, that G is 0, right? And I know at B, G is 0, yes? So if I have a function that's 0 at both ends, then it either has a max or a min in between. Therefore, there's a point in between whose what? Whose first derivative is 0. So I don't know where that point is. Maybe it's here. There's a place, g prime of c, which is 0. Yes? But what do you know about g prime at a? It's also 0. Right? Okay. Good. So I have a place where g prime is 0 and at a and at c. Therefore, good. There's a place in between where the second derivative is 0, which is the derivative of g prime, which I'm assuming exists because we are assuming this has enough derivatives to keep taking derivatives. Oh, somewhere between these two, yeah? Maybe here. Let's call this C1. There's a place where C2 is 0. Okay, help? Yeah, so what I'm saying is there exists a C1. There exists a C2. Continue. What do I know about g prime at A? It's also 0. Therefore, there exists another place in between C3 where g prime of C3 is 0, etc. Keep going. How far can I keep going? Good. So by the time I get down to, let's see, the last step here, what will I have? Well, the very last step is you go to the n minus 1th place derivative, and then you you postulate there's a point in between where the nth derivative at some point c, I guess this is the one that's Cn, right? This is the one you want to call C, is 0. There exists a C n such that this creature is 0. Okay. And now, is that what I wanted to show? Is that what I wanted to show? Yeah, this is what I wanted to show. Okay, so, oh, nice, nice. What is the upshot? Why does that show that f is p plus this creature? What's that? Yes. So I can plug this back into Cyclops Smiley, and now Cyclops Smiley is true. Here you can view B as the point I'm interested in, right? So B here is playing the role of this x. Okay. You want to know what f of B is in relation to Pn minus 1 of B, then that's where Cyclops Smiley finishes the argument. Okay, so if this were 0, then we solve for m. That's right. And if we solve for m, then f of b will hold for that m. So let me just make sure I get this in here. So this shows m is, in fact, fn of c over n factorial. Then in Smiley, we get the result. Okay. Okay, this is actually, I like this proof a little better than the one that's in Rudin. Yeah, I like this one better. Of course, we're using the mean value theorem several times here, yes? Basically bootstrapping down these derivatives through a clever choice of function. Now, of course, you're seeing very, very, very slick arguments here, and I should just warn you that you're seeing basically the product of many, many decades of people thinking of better and better proofs. Okay, the original proof of Taylor's theorem of mean value theorem due to Cauchy, 1823, is actually wrong. Okay, there's some issues with the proof, and it wasn't really gotten right until I think it was Bonnet in the 1860s actually had the first valid proof of the mean value theorem. Question?
I don't know. The way the theorem is stated, it seems like the C is fixed for all x, but doesn't the C change for each x?
Let's see. So your question here is C could depend on x. C actually here depends on, C could depend on the point x. Let's see here. Sorry, did I write this correctly? So we have a function. We want to establish. Yeah, so I should, right, so C could depend on x. Maybe I should make that clear here for some C. And this may depend on x. Actually, in fact, what we've shown is that this C lives in between A and x. Maybe this last point B could even, this last point b could even be changed to x, if that helps. Let's see, do I buy that? Is that what I want to say? X is over and c is in between? Yeah. Could even depend on. Now this clearly depends on, could clearly depend on x. It certainly lives between a and b. Yeah. But the c could change. Yeah? Does that address your issue? You were trying to correspond the two, right? Yeah. Okay, excellent. So that's the content of Taylor's theorem, and you'll note a few examples in the homework where you're going to use basically all the homework problems involve the mean value theorem or Taylor's theorem applied in some way, some clever way, usually. All right. Okay, great. So let's take a couple-minute break, and after the break, I want to talk about sequences of functions. Let's resume. So we've spent the first 5 chapters of Rudin basically building up a lot of machinery. We've built up machinery that allows us to think about the real numbers carefully. We also built up machinery that helped us think about functions carefully, what it means for a function to be continuous, what it means for a function to be differentiable. What I want to do with the remainder of this lecture is sort of point towards some ideas that you're going to encounter if you take analysis 2. And that is, one of the big ideas is, it's not just the real numbers or Rn that we're interested in. You know, we built up all this machinery about metric spaces. What's it useful for? Okay. So one of the big places where it's used is thinking about functions as living as a metric space living in their own metric space. And so I want to talk about sequences of functions. And this is actually one of the main motivations of analysis. So we've said what it means for points to converge, but what does it mean for a sequence of functions to converge? So for instance, I might have a sequence f1 of x, f2 of x, etc., f3 of x. What does it mean for a sequence of functions to converge? So here I'm thinking about the functions as real-valued functions. But what would you say it means for a sequence of functions to converge? Like, maybe I have functions like this and like this, and rather boring example. What would it mean for this sequence of functions to converge? What would you give me a notion of convergence here? Katie?
Keep getting closer to one specific function, so the values for each point go closer to a single point.
Okay. So, for instance, take some points here, fix a point that you're looking at, and see if they converge to something. Is that sort of what you're saying? Right? Okay, good. And do that for each one of these. Right? And then I'll have some limiting function, perhaps, that this creates. Yes? Okay. Yeah, so one way to answer this question is pointwise convergence. This is what we call pointwise convergence. Basically, fix x, and then ask yourself, does fn at x as a sequence now evaluated at a particular point converge? If it does, we say it converges pointwise, and we give it a name. We say it has a pointwise limit, which is just what you think it is, namely f of x is the limit of fn at x as n goes to infinity. That is a sequence of numbers, after all, right? So I'm calling this limiting function f. If this limit exists for every x. Okay? Okay, let's explore this idea. Tell me what the pointwise limit of this sequence is. Example 1. How about, oops, oh, can't even draw these. Here's a sequence of functions, and here the functions are fn at x is x divided by n. Does this converge pointwise? To what? To the 0 function. This is the function 0, right? In fact, I'll write this like this, f of x equals 0. Yes? Okay, very good. Pointwise. Okay, we'll come back to that example. What about this function? How about f sub n of x equals x to the n, and we're now limiting ourselves to the domain 0, 1, not the whole real line. Does this converge pointwise? Let's see. What is f1? X, yeah? Yes? What's f2? X squared. What's f3? X cubed. What's f4? X to the 4th, etc. Does this converge pointwise? Yeah? To what? Zero? What about at 1? It stays at 1 for 1, and everywhere else? 0. Ooh, interesting. So it converges pointwise. Yes, but to the function f of x equals 1 at x, if x equals 1, and 0 else. On 0, 1 only. Okay? Interesting. Let's look at another example. How about example 3? What if I have this function? This is the function that has got a spike. And the spike is at height 1, and it's supported on n minus 1 and an n plus 1. So the spike is at n, and it lives between the next two integers. So f1 is over here, f2 is over here, f3 is over here, f4 is over here, etc. Okay? So help. What does fn converge to? Does it? What does it converge to? Pointwise, if I look at a particular, let's look at pi. What is it doing? It's 0, 0, something, 0, something, 0, 0, 0, 0, 0. Would you agree? Pointwise, all these things converge to what? Good. Interesting. Interesting notion of convergence. Is it the right notion? Is it the best notion of convergence? What if I look at this function? How about f sub n at x is 1 over n sine n squared x? Okay, what's that doing? Well, okay. I'm just going to roughly draw something. Here's the first one, yeah? The second one has what amplitude? Smaller, right? And then what frequency? Bigger, yeah? Okay, so it might do something like this. And then the next one, even more frequency, like this. What does this converge to? Yes, you're right, also the 0 function. Don't be fooled, not all sequences of functions converge to 0. It just was easier examples to construct, obviously. Okay. But what can you learn from these examples? This sort of points out some very, very interesting behavior. Well, I mean, here's the kind of question we've been dealing with. when you have sequences, what properties are preserved by the limiting operation for functions? What properties are preserved by limits? By pointwise limits. I mean, for instance, is it true that the pointwise limit of a continuous function is continuous? No. Why? See example 2. Oh, okay. What about what about derivatives? If I take the derivative of a limit, is the limit of the derivatives? And a very good example of this is in physics, where you have an infinite sum and you're asked to take the derivative of an infinite sum and you do it term by term. Wouldn't you agree an infinite sum is like a limit? Okay, so are derivatives preserved by limits? You think? No. In fact, here, these derivatives, you can see, are starting to behave very wildly, and their limit, limiting derivative of the limit is 0. This is not in general true. What about derivatives? What about integrals? So think of areas. Are they preserved by pointwise limits? No. Example 3. Does not. This notion of limit is actually it's not such a. It doesn't have nice properties, does it? With respect to a lot of the things we care about. So this points out the fact that we actually need a stronger notion then to help us. That it will maybe help some of our issues here. Okay, not all of our issues, but some of our issues. And exactly what issues they'll help with is I'm going to leave to much to analysis 2, Math 132. But let's look at a stronger notion. Let's look at the supremum norm of a function, which is defined to be, tell me the function value and take its supremum at all points in the domain of the function. Okay, so let's take its supremum of the absolute value. Okay. Okay, so for instance, the sup of this function would be what? 1. The sup of this function over the entire domain? Yeah, infinite. Yeah, we don't like that, okay? If I restricted my domain, you could see the function would actually have a supremum. Okay? Okay. So, interesting. Well, let's make a definition. So the definition will be a different kind of convergence, and it's called uniform convergence. Not to be confused with uniform continuity. Completely different concept. But the word uniform is supposed to make us think of what? Well, everybody's wearing the same uniform, right? Okay. So what is that? What's behaving uniformly here? We're going to say f of n converges to f uniformly, and I'll put a little u over the arrow. And we'll say f converges uniformly to fn converges uniformly to f on E if for all epsilon bigger than 0 there exists an n such that little n bigger than big N implies the norm of fn minus f is less than epsilon. Okay, so question. How is this like or different than the notion of convergence, the notions of convergence you've seen before? Katie?
It preserves the peaks, like on example 3, it preserves the fact that there's a peak there, so you can't just
Okay. We'll come to this example in a second, but I think what you're saying is this sequence would not converge to 0 uniformly. What's uniform about this definition? Give you a hint. I'm taking a supremum here of differences. How is this definition different than pointwise limits, which also ask you to take a limit of a sequence? Jenny?
You're saying that all points in F have to be close to all points after a certain point, as opposed to, if in example 1, they all eventually go to 0, but some are still really, really far away from 0 at each step.
Excellent. So the idea here, because we're looking at the supremum of a difference, and we're demanding that be less than epsilon, is we're going to have ribbon convergence. So this is the way I like to think about it. You're trying to, so you can draw an epsilon ribbon about the limit f and fn is eventually stays in the ribbon. What's uniform is it's the same n works for every x. The same n works for all x in E. Okay. So just to look at our example here, let's draw a little ribbon and see what happens. Suppose I draw, so would you say that this sequence converges uniformly to the limit? No, these functions are not all living in the ribbon eventually. In fact, every single function eventually leaves this ribbon. Yes? Epsilon ribbon. Okay. Does this function converge uniformly? This sequence converge uniformly? No. Yeah, you'll have problems still no matter how far you go. You'll have problems where this function does not live completely inside, right? Okay. What about this sequence? No, doesn't converge uniformly. What about this one? Oh, yes, this one does. Okay. So not all our problems are going to be solved by this notion of ribbon convergence, uniform convergence. Okay. In particular, you'll see not all of them will be solved, but maybe some of them will be. That's the question. Now, the thing you should notice about this is I've really just disguised this, but really what I've just done is I've placed all the functions in their own metric space. And I've given the distance in the metric space of functions to be basically a supremum distance, right? So this is just convergence, is just the usual convergence in the metric space, which I'll call C sub B of E. This is the continuous bounded functions on E. The C stands for continuous. The B stands for bounded functions on E, real valued functions on E. So really, isn't this just the metric, the distance between f and f? I'm just letting it be the distance between f and g to be the norm of their difference, f minus g. Okay. So, what's so great about this metric space? It's a metric space, right? What's cool? That's what's great about it. It's a metric space. Look, there are points in here. There's f1, f2, F3, I'm thinking about every function as a point in its own space. Yay. Okay, yes.
Why are we only looking at continuous bounded functions?
Well, yeah, so certainly you could define this notion, if you like, on larger spaces of functions, but this is one class of spaces where it's convenient. Okay, you could certainly define in larger spaces. You'll have a problem defining the notion of the supremum on functions that aren't bounded, but certainly you could define it on something that's maybe not continuous. Yeah. Okay, points in their own space. Question. Well, okay, so uniform convergence is just like regular convergence in this space. Well, let's see. Suppose I have a bunch of functions. Must they have a sequence? Must a sequence converge? Not necessarily. Well, what would you like to know about this space, for instance, for a sequence to converge? Is it complete? There's a question. And here's a big fact from analysis 2, which you'll prove in analysis 2. This, in particular, this space of functions, CB of E, is complete. Very nice. So, in fact, we have a Cauchy criterion, which will allow us to say, without knowing what the limit is, whether a limit exists. Let's just see if the functions converge. If the functions form a Cauchy sequence. So the Cauchy criterion, here's the theorem. Fn converges uniformly to F on E if and only if, well, okay, just no surprises here. For every epsilon bigger than 0, there exists an n such that for all n and m bigger than big N, and for all x and e, the distance between fn of x minus fm at x is less than epsilon. Notice I've just replaced the double norm signs by saying this is true for all x and e. It's the same thing. This is a Cauchy criterion for uniform convergence. Oh, nice. Very nice. So, so look at what this means. Suppose I look at this sequence of functions. Let's how about the first sequence? First function, this is a function. I'm going to define this function going from 0, 1 into the plane R2. So it's a path, right? Here's one path. Oh, I didn't say actually what the image here of this sequence is, but it's true for even when the image is not the real line, but in Rn. So that's what this example is. Here's the first path, F0. Let's make that F1. Okay. That's one function. Let me define another function. How about this one, F2? Let me define another one. How about this function, F3? Oh, let's define another function. How about F4? Okay, don't make me do all of these. Now, what some of you have seen as construction, this is a construction of, the Koch snowflake. And it's a fractal-like construction, right? But what do people say the snowflake is? Well, it's the one you get by taking the limit of these functions. But wait, how do we know the limit exists? Cauchy? Why is this sequence Cauchy? Successive distances are smaller and smaller. In fact, past some point, for a fixed x, all these terms are going to be close. And you can define the function carefully so that at a half, it's always here. So half, it stays put, and at 1/4, it stays put, and at 3/4, it stays put, and then extend linearly, right? So what do you have? Fn here, like so. I'm not going to write out those things, right? You can see by construction, it's Cauchy. So it converges. Amazing. I know the limit exists. That fractal limit exists. Okay, now of course the next question is, what is its limit? What is the limit? That's another question. What can I say about the limit? Well, here's another amazing theorem. Oh, this gets so great. This is awesome. Look, turns out that if you have a function that converges, sequence that converges uniformly to a function f, and the fn's are all continuous, guess what? The limiting function is continuous. Is that true in general for pointwise convergence? No, but it is true for uniform convergence. The ribbon convergence helps us, means that the limit is, in fact, continuous. And what does that mean for the snowflake here, construction? The limiting function is continuous, right? It's continuous. Right? Because of this theorem. We can actually prove this theorem. So let's do that. Well, let's see. How am I going to argue that the limiting function is continuous? Well, would you agree the idea here is to use the following bound. I want to bound the distance between f of x and f of y, yes? I want this to be small. What do I know is small? For a particular fn, I know fn of x and fn of y is small. And I know the distance from f to fn can be made small. So the bound is going to be, it's a classic epsilon over 3 argument. I'm going to look at the distance from f to some fn, and I have not said which one yet. Compare that to the distance from fn at x to fn at y. And then compare that to, help, fn at y to f of y. So we're going to use this bound, which I'm going to refer to as star. I know you wanted a smiley. But I'm going to refer to each of these pieces as cyclops smiley, double smiley, and triple smiley, because I'm going to refer to them. That's the operative bound. Okay, we can do this. We just got to make our choices carefully. So let's fix x, the one we're talking about. So we'll show continuity at x. Now, so for all epsilon bigger than 0, by 1, we'll choose, what's 1? Oh, this is the steps of the proof. We'll choose f sub k so that what's small? Or f sub n so that what's small? So that f sub n minus f is less than what? Let's make it epsilon over 3. Okay? So what this implies then is that cyclops and triple smiley are both less than epsilon over 3. Right? That's the first choice that needs to be made. Good. What's the second choice? Well, what can I say about fn? It's continuous. So for this epsilon, there exists a delta bigger than 0, and I need to say what epsilon because I'm about to refer to it. There's a delta bigger than 0 such that if the distance between x and y is less than delta, then what? double smiley is small. Less than what? Epsilon over 3, because you could make that anything you wanted, right? Oh, okay. So what am I looking for? For this epsilon, I'm looking for a delta that works for f. What delta will work for f? The same one that worked for Fn. So we found a delta bigger than 0 such that f sub x minus f sub y is less than epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is epsilon, as desired. Our function, our limiting function, is continuous. Okay, so as a last application, here's an amazing fact. I claim there exists a function from the interval into the box. What box? The square. That is space filling. What do I mean by that? This is what's called a space filling curve. I claim there is a function from the interval into a box that completely fills out the entire box. It hits every point. What? How's that possible? I mean, look, this is a compact interval, and you're saying this is going to fill out the whole thing? What? Well, it's very easy to show using this theorem, because I'll just construct this space-filling curve as a limit of sequence of functions that is uniformly convergent. And I'll do this by making it Cauchy. Oh, this is so great. Look, here's a first function. This one's very easy. I'm basically just going to divide this up into thirds, yeah? I'll just wind my way through like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? There's lots of ways to do this. I'm just showing you one, right? That's the first function, f1. Oh, okay. How about the next one, f2? I'm basically going to now just cut each of these up into tic-tac-toe grid and replace each of those lines by the same construction, little butterfly. Yeah? Then I'll go this way here. Oh, no. Okay. Etc. I really don't want to do this forever. But you get the point, yes? Now, for each of those, split them up and do it again. Okay? Construct the function that basically passes through these points at exactly the same time. Every corner points pass through the same time, but you just blow out the inner part. Okay? Now, why is this actually converging uniformly? Well, you can convince yourself, like you can there, that everything stays within a little box. All the images of particular points for a fixed time stay within a little box past some point. So it converges uniformly. So it converges in a Cauchy sense. So it must converge to a limit. And that limit, you can show every point in this box is actually the limit of the pointwise limit of some point. Okay? So it fills out all of space. It's an amazing fact. There exists a space-filling curve. Yes, question? Can you fill out in 3 space? What do you think? Yes. Yeah, you can fill out a space. You can probably figure out a good construction for that as well. Yeah. Rn? Isn't that neat? That is so neat. Okay. So there's lots coming in analysis too.